Variable measurement. So there are a set of ways to measure the variables of the things we want to observe in the world. And here I have a list of the major ones. The first one is the nominal, or the qualitative representation of a category or label of an individual. Once again, we're using these terms very broadly. Individual is any of the individual thing you're measuring, be it object, people, feeling, thoughts, processes, and so on. So for example, an example of a nominal variable may be color. Color is usually nominal, although sometimes color may be quantified as well. But often we're going to find color as a variable that is nominal, and it has a set of potential categorical values such as red, blue, white, orange, and green, or something like that. The ordinal variable is a semi-quantitative variable. It's essentially categories, but in some kind of descending or ascending order. So for example, let's follow along with the B example here. If we want to measure B, one of the variables is color. So I don't have it listed over here, but it could be one of these, color. We want to measure the color of the bee. One variable may be a flight technique, or a flight, some kind of flight performance of the bee to see if they're flying well. And you may measure this variable as either poor, okay, or good. So these three category ordinal variable. So although they are categorical and nominal, there is some relation of ascending or descending between them, right? To the right is better, which doesn't exist in the purely nominal type of variable. Another kind of variable measurement is via interval, which is a quantitative measure with possible quantitative differences between values. So the interval is usually just going to look like an integer, and it may even be a decimal as well. So not just integer, but decimal values. And so it's very similar to the ratio as well, which we're going to be talking about. And the difference is that the interval, the difference between values makes sense numerically. So for example, year observed, let's say the year that we observed the bees, maybe 2010, 2011, 2013. And we can actually carry out mathematical manipulations on these numbers, like 2011 minus 2010 equals 1 year difference. We can observe the differences. But once we get to the 0, and the 0 is the key thing here, is that when we get to year 0 is not actually no year at all. Year 0 is a particular year. So it kind of gets complicated if you want trying to do other kinds of mathematical manipulations. And that's why we differentiate the interval from the ratio. The ratio is the quantitative measure that does have a true 0. And we can actually use years of age, which is actually similar to year, right? Year observed, years of age, but distinctly different in this one sense. The year observed doesn't have a true 0 in the sense that year 0, it doesn't mean no year at all. It's just a particular year, the way we're counting. Years of age, 0 years though, does mean no years at all. So, but an individual can have 1 year, 2.5 years, 3 years, or no year at all, which is 0. So these are some of the main ways to measure the attributes of the things we're interested in. Now, when we're talking about variable measurement, we're also talking about data type, because the variable measurement translates to the data type that is recorded in the computer, in the digital format of the computer. So you got to be aware of both the variable measurement and the data type. So nominal variables are usually translated to data type as called text, character, or string. These are usually just the same, different name for the same thing. Depending on the program you're using, they may have a different reference, but usually these is text or character data. So essentially any letters or numbers are valid. ordinal may be translated into, we may have a data type that is text or character, but we also actually often happens is if we do have an ordinal variable, we will translate that into some kind of integer, such as -1, 0, and 1 as the possible values. And then we will just write somewhere in the metadata and the explanation of the data that -1 refers to poor, 0 refers to okay, 1 refers to good. And of course, because you can imagine, we can keep adding 2, 2 is great, and then -2 is really poor. Now, this can be more or less sort of appropriate, but this is what often happens. Interval is usually data type integer, but I think actually the interval can be decimal as well, conceivably. So for example, temperature. Temperature is interval, it doesn't really have a true 0, but we can talk about 7.5 degrees Fahrenheit. So decimal is also a potential data type for interval data. And the ratio, which is essentially any of the real values, 0, 1s, fractions, or integers, and the data types are going to be decimal, double, or float. These are also all names, usually names the same thing, although depending on the computer program you're using, double may be slightly different than float. For our purposes here, these are just numbers or fractions, including which means decimal numbers as well. Now, another kind of data type that we need to talk about, or a variable measurement as well, is the binary. And binary measure is a measure that has two values. So presence or absence, true or false. So for example, a variable, let's say called carnivore, may have the values yes or no. So carnivore is, you can think of it as could be a value of another categorical variable, such as a type of eating or eating behavior. But then we can translate the categorical variable itself into a binary, carnivore, yes or no. And then when we do that, the data type is probably going to be binary, because binary is the native data type of computer. So that's just 1 or 0, 1 yes, 0 is no. Binary data is special for that reason, because any number category may be translated into binary, which is itself numerical. So binary data is 1 or 0, so that's kind of numerical. So so any kind of category like male, so let's say gender or sex, can be instead of, we could have, let's say, sex as the name of the attribute, and it has two potential values, male or female. So this would be a categorical variable of two values, two categorical or nominal values. Now, instead of that, we can do the same thing. We can do the same, get away with having the same information, but instead call this variable male, and then just say if it's 1 for yes or 0 for no. So we just turned a nominal variable into a numeric variable, and it's a beautiful thing and enables all kinds of interesting analyses and learning about the world. Has 6 legs. Actually, that's a bad example, because if you're just trying to find out legs, you just would write, legs and how many legs, 6, 3, 2, 4, 5, and so on. So this would probably be a quantitative variable. But color, red color, for example, true or false, and then you can just continue on. So you're translating color into a blue, true or false. Once again, translating the nominal variable into binary, which is numerical. Let's talk about sampling techniques. So sampling is the process of selecting a subset of individuals from a population to be studied. The most basic technique is the simple random sample. This is when a subset of a population is selected where every individual has an equal chance of being selected. So how does this happen? So let's use this example here. Suppose you have 50 states to study. You want to study how bees appear across the 50 United States, but you don't really have time to go on all the 50 states. So you say, okay, I can only have enough funds to look at 15 states. So to get a random sample of 15 states, what we're going to do is we're going to add the names of all the 50 states into separate small pieces of paper. We're going to fold these papers and hide them and throw and make sure they all kind of look the same and feel the same and the same size and so on. So they have an equal chance of being selected. And then we're going to throw them in a hat. We're going to mix it real well. And then we're going to draw 50 names from the hat, and voila, we have our random sample. Now, this may seem very crude and analog, but that's actually a legitimate way of getting a random sample. And it's kind of a beautiful thing too, because it relates these abstract mathematical concepts to just the kind of messiness of the world. So the idea is that there is an equal chance of being selected because we want a random sample, usually from the population. So there are many other sampling techniques, all of which involve some aspect of randomness. So suppose you did this process here. I put them in the hat and I identify 15 states. But it just so happened you did this once, and all of the data, all of the states you got were both in the Northeast and Midwest region. And you may say, wow, how is that possible? I thought it was random. And because it was random, I thought you would get a little bit from each, right? The chances are that I would get a little bit from each region of the state, not just two regions. And theoretically, that's true. However, any one occasion that happens, the one time you did it, it just so happens that there is a chance that you will only get states from two regions. So instead of doing this process over and over until you find a satisfiable distribution of states across all of the regions, what you may do is something called stratified sampling. So to ensure you select a few states from every region in your sampling, you may first separate the states into regions. So maybe you separate like, different hats, one hat, 1, 2, if you need, let's say, I need at least 4 regions. So you have 4 hats and you 4 hats of each. So only the states in this region go in here, only the states in this region go in here. And you take a few, 4 or 3 from each region and so on. And you ensure that you're getting at least a few from every region. Why do we want to make sure there is randomness in the sampling technique? You can pause the video now and think about it for a second. I'll tell you the answer. The reason we want randomness essentially is to avoid bias. So usually if we want to understand the patterns of a population and we only have a sample, we want to make sure that the sample accurately reflects the population. So if you want to discover how the bees conditions are in the United States, you want to make sure that your data is for the whole United States and not just from the Northeast. If you have just bees from the Northeast, then your data is going to be biased or skewed or perhaps just completely reflecting only the Northeast. So randomness is the process by which every piece of individual that you're trying to select has an equal chance of appearing. And we want to employ randomness because we want to have a sample that reflects the whole population. The data set. The data set is the set of records collected for a study. The data set is also called the data or the data set. It may be a population or a sample of the relevant individuals, as we're kind of just discussing. And that's actually kind of an interesting example here when we talk about the cases of COVID-19. So we can have a data set of confirmed COVID-19 cases as the population of confirmed COVID-19 cases. That is, we may be reasonable to expect that all of the confirmed COVID-19 cases are in the data set we're looking at, maybe from the CDC. And that's because every confirmed COVID-19 case is strictly reported by the CDC, and therefore they have every single confirmed COVID-19 case in their database. Now, this the confirmed COVID-19 cases, so, and I kind of emphasize here, the confirmed COVID-19 cases is naturally going to be only a sample of all population of all COVID-19 cases, because just by the nature of a pandemic or an infection like the virus COVID-19 or the coronavirus that causes COVID-19, not all cases are going to be confirmed because people don't know or because people don't test and so on. So the confirmed COVID-19 cases is a kind of sample of the entire population of COVID-19 cases. The data set, as mentioned, is usually one or more tables structured in a table of rows or columns or tables. So the table is the thing, object, or phenomenon being analyzed. Here I just have an example of a set of tweets from a public health agency. And so the table itself, or the data set, is going to be, well, set of tweets. And then set is ambiguous, but maybe is a sample. Actually, here I have the population. I have all of the tweets, and I know for sure because, well, not 100%. It's always difficult to know 100%, but I know that this is probably pretty close to the population of tweets from agency X, XYZ, ANC Public Health. Within, and then it gets, of course, always gets a little bit more specific, within, you know, year 2020. Oops. So the table is this, the population of tweets. So the rows are the instances of the table. So each row is a tweet. Each row is a tweet. Each row is not an agency. You're going to see the agency name here. Also, we have the text of the tweet itself. We have the number of likes and so on, the number of retweets. But each row is not a retweet. Each row is not an ID, even though there is an ID here. Each row is a tweet. So that's very important to remember. That's one of the most basic things about looking at it and analyzing the data. And the columns, once again, are usually the fields, also called attributes, features, variables, and so on. Here's just a bigger picture. You can take a look at it. And we'll discuss this more deeply as we go. In particular, I wanted to bring attention to null values, or NA values. So null values are a special kind of value, often abbreviated as NA or sometimes just empty. And null or NA values can have several meanings. That's why they're kind of annoying and we don't usually like them. So sometimes NA values means that zero or non-existent. So for example, let's say there's a tweet here. This tweet from the agency says, tonight at 5 p.m., come together, blah, blah, blah. That's the text itself. Now there is one attribute here that is reply to screen name, like the person or entity to which this tweet is being replied. And here it says NA. Now, because of the nature of this data, I know that NA means that this is not a reply to anybody. There is no reply to somebody because this is not a reply. So in this case, NAs are not that complicated or big a deal, but the problem is that NA could also mean that someone forgot to include the data there, or that they didn't have that value at that time, but later they did have it, or that they never had it. So once again, this information may be available in the data set metadata. So in the more description of the data, what the NA value means, it would be great to be described there, but not always. Often though, remember that NA values may need to be excluded from analysis because you don't know what it is. It doesn't automatically mean zero or just false or something like that. So it always depends, and it's something to pay attention to. The unit of analysis. I'm just going to emphasize this point here, kind of maybe a repetition, but because it is so basic, I wanted to make sure that we understand the unit of analysis. And the unit of analysis is the level at which the individual data record is being recorded. So this may be an individual, an object, or a phenomenon. Phenomena, I just use this word very broadly to mean essentially anything, any process, any idea, any concept, any spirit, any event, and so on. Notice though, the unit of analysis can be a component of an individual or object or phenomena, or it can be a generalization of an individual object or phenomena. So maybe we could have a data of agencies that tweet. And maybe we'd have multiple agencies over here and so on. Here, I only see one, but the agency name is here. I know there is an agency, different health agencies here, but this data set is not a data set of agencies that tweet, even though that information is here. This is a data set of unique individual tweets. So identifying the unit of analysis, the unit of the thing you're observing is very important, because these are the individuals or your data instances. Here's just another example from the B data set that I've been talking about. You can take a look at it yourself if you have time, from the USDA. And you can see that they're collecting, and actually it's kind of a little bit complicated data set. So I may not use it for this class for exercise, but it's interesting to study it, because this data set refers to occurrence of the bees. So every record is an occurrence. So is that one bee, or is that a site of a bee, or is that occurrence? How was the occurrence measured? And to be honest, I couldn't figure out from this data set, and this is why I avoided using it. So often this is an issue to be addressed, but it's important to know that nevertheless. Next, we'll talk about two basic approaches to statistics and data distributions.